All right, so I'm actually done this video like a few times. Keep getting confused about certain things, but I'm gonna try to make it right this time. So, what is so confusing about number one is that people can take these different scenarios and write them in all sorts of ways, and they could switch what's meant by systems and surroundings, which means it's important to map out what exactly is happening. So, here's the thing: if energy, or you could think about energy as being heat, is leaving a system and going into the surroundings, that's exothermic. And the opposite of that is endothermic, which means energy is going into the system. So, with these diagrams here, first I'll explain the direction of the arrow. So, you have the can. This is the can, which they're defining as the surroundings. That's getting colder, which means energy is leaving it and going somewhere else. So, the somewhere else will be the system. Surroundings and systems are opposites of each other. So whatever is not the surroundings is the system and vice versa. So if energy is going into the system, that's the definition of endothermic. That's why I chose that one. Next one, water is placed into a freezer, forms ice cubes. So water is the system this time. And what we have is the water is getting colder to become an ice cube, which means that energy has to leave it, heat has to leave it. So it's going to go into the surroundings. So the definition of exothermic is heat or energy going to the surroundings. I'm using those words heat and energy interchangeably because they are actually the same thing. C is probably the most confusing one because it's talking about melting, but they're defining the calcium chloride as being the system, whereas we would normally think about that as just being like a portion of it. So that's like the salt that they're going to put on the roads tomorrow. So in this case, you have the this is the one question where I keep changing my mind on. I think I'm gonna change it this time. So the ice is has to be absorbing the heat. So I'm deciding now that it should really be going this way. If you're defining the calcium chloride as being the system, the heat is leaving the system and going into the surroundings, which is the ice. So I'm going to say this one's exothermic. Apologize for that. Okay, so let's move on. Now, this one I had to look up a lot of stuff for. There's a lot of different words here, but you have to be careful with looking up things because of the direction, which is the exact same problem I was having with the other one. You'll see what I mean when we get to this last one, lattice energy. All right, so enthalpy of sublimation. In short, that means turning something from a solid to a gas. The best example here is dry ice. Dry ice is looks like ice, but it's actually carbon dioxide solid, and it goes straight to a gas instead of passing through being liquid. So what's happening is that requires energy. You need to put heat into the system. You need to put energy into the system, which is definition of endothermic. Ionization energy, you might want to just memorize what happens here rather than getting into all the atomic stuff with electrons and whatnot. But what it's saying here is that when something gains an electron, so well, it's not actually gaining an electron. What's happening is you're taking a, let's just say it's an atom there. You're turning it into an ion and off shoots an electron. In order to make that happen, it requires energy. You're breaking something up there, it requires energy. Enthalpy of dissociation. Let's look at what's happening here. So we got forget about the coefficients, it's not important right now. What matters is this and this. This one here is a molecule. This here is an atom. So you're turning a molecule into an atom. Just think about if you had any sort of diatomic gas, like nitrogen, and you're turning into two nitrogen molecules, this and this. You're breaking a bond. When bonds are broken, you need energy to do that. It absorbs energy, therefore it's endothermic. And note that the first three there, if you are doing the reverse of it, like if the equation is just the mirror image of it, it's going to be the opposite answer. Electron affinity. So here we're taking an atom, adding an electron, and we're turning it into an ion. This is actually the opposite of this. So these two go hand in hand. And so if they're the opposite of each other, the opposite procedure, it's going to be doing the opposite one of these two words here. So therefore it's exothermic, releases energy rather than absorbs it. Last one here again, direction is really important. If you were to look up lattice energy online and say lattice energy, endothermic or exothermic, you'll probably get two different answers. So it matters what exactly is happening. Are we taking something and breaking it up into ions, or are we taking ions and making something? We're doing the second of those two. So this is kind of like if you took sodium, like a sodium ion, and you combined it with a chlorine ion to form sodium chloride, which is table salt. That is forming a lattice. So a lattice is a structure. We use the word lattice in chemistry to mean structures of all different kinds of things, but a lot of times salts that releases energy. So that would be exothermic. So to a certain extent, you might want to memorize some of these, but pay close attention to the direction. And moving on. Next one's pretty simple if you just read it carefully. So oranges are sprayed with water. That seems to look counterintuitive because when we spray ourselves with water and go outside in the freezing cold, it's cold. But it actually protects the oranges. I'll see why here. So let's start with B. I'm going to read B first. The water protects the orange trees by freezing before the oranges do. That makes sense. Right, so you have the cold. The cold is going to contact the water first. But that's not kind of the proper way of thinking about things with exothermic, endothermic, because cold does not. That's not really a concept. The concept we use is heat and energy and the direction that is moving. And second part sentence, the process of freezing absorbs heat. That just doesn't sound right. That makes this answer not make sense. If you're freezing something, it's removing heat from it. So we want to go with A, which the only difference between A and B, I think, is that word. Heat absorbs, so they don't freeze. We'll see more of this concept in the next few questions. All right, methane combusts. So combustion is combining with oxygen. When we think about combustion, like spontaneous combustion, we think about things like blowing up or burning. Well, that's what oxygen does. Oxygen is flammable. So where are my drilling tools? There you go. This one is talking about 25 degrees Celsius. They're bringing it up because if it was a different temperature, the same process would still happen. Just it would happen with more energy. Remember, temperature is related to energy. Temperature itself is the kinetic energy of the molecules. So if you look at the two diagrams, one has more activation energy than the other one. I want to pick the one with less because it's less temperature. And how you know that this part that I label in pink is the activation energy, I would just encourage you to look at the diagrams in the sections. Your teacher's notes are actually really pretty good, and the diagrams are helpful to understand what's going on. A lot of this, when you just see these curves here, just draw these dotted lines to figure out what's going on and see the relative sizes of things. All I want to say about that. So it takes a while to switch these sometimes. Okay, a few things about this. We have a decomposition of something, we don't know what it is, and it says two possible reaction pathways. That means two ways to make the process happen. For example, you can have it just happen naturally, or maybe use the catalyst. But you'll see that the end doesn't matter. If you do it, the start and the finish for both of these is the same. They come together. They come together like right around here. Is this reaction endothermic or exothermic? So you can compare these to the diagrams and kind of memorize what's happening with the diagrams. That's one way to do it. Other ways to think about the total change in enthalpy. Total change in enthalpy is this H here. That's the difference between the start and the finish. If something is gaining energy going into the system, it looks like what's happening here. Notice that the end line is higher than the start line, which means it gained energy. When something gains energy like that, it's endothermic. The prefix actually helps here. We don't really use the prefix endo in everyday life, but we do use like exo, like outside. Can't think of a good example of this now that I said that, but X means out, exit. But that was stupid. Exit. All right, so this is like heat exiting, exothermic. Well, the heat is not exiting; it's going into it. The energy is going into it because it's going up from here to here. So it makes it endothermic. B, describe the direction of heat flow. That's kind of just what I said. Heat flows from the surroundings to the system. It's absorbed. Note it's going to be a positive value. Okay, so it's positive 120. I think it's going to come up in question 3 second. All right, here we go. Number 3, why would path 2 require less energy than path 1? Well, even though they wind up the same amount, the activation energy is different. Okay, so I put for 3A, I don't really know how else to explain it other than saying the activation energy is different based on the graph, because we don't know any other information about this. We don't even know what this is. Let's take a look at where I got those numbers from. So for path 1, the activation energy is shown here. So activation energy is the difference from the start to the highest peak. That number is given, it's 220. For path 2, it's not given, but it is this amount right here. So again, that's activation energy is the difference from the start to the peak right here. Just to add up these two numbers to get this 180. The activation energy of the reverse reaction. And for the reverse, you can look at it in reverse. I'm going to kind of draw like a rough picture about what that would look like. So the finish will be the start. So I'm going to go, what's it asking for? Yeah, I assume they're talking about path 2. So we're going to go this way, like that. All right, so I'm going to start off with something and go up and then wind up lower rather than higher. So there still is activation energy right here. And if I look at what that is, that's going to be this. It's a little confusing, but just take a second to look at that yourself to see why that is here. This is going to be the same as this when you flip it around. And D, what happens to change in H? Now, what is that's delta H, the triangle delta H, change in H? What is that? That is enthalpy. So enthalpy is that value I keep talking about being the total change in energy of the system. We just have a separate word for it because it's easier to talk about, I guess. Because enthalpy is just specific to chemistry. If you look at paths 1 and 2, they have the same start and the same finish, which means they're going to have the same change in enthalpy. It doesn't matter what the path is, independent of path. That is a fact. And the last one, I'm going to bring up another picture because I think it'll be bigger. And I know this is all still very confusing. A lot of there's quite a bit of memorization in this section of graphs, but definitely make sure to take time to understand the graphs. The one I always use more memorization with is all those those words with the number two in the previous section. All right, dissolution of ammonia. All right, so let's think about the direction of this one. This one's like a little counterintuitive too. We have to do before you do the graph. The graph is easy. We just kind of copy here. We want to do all of this. Want to determine what kind of reaction it is. What is happening? I'm showing energy going into the ice bag. That kind of sounds like heat is going into the ice bag. And that is actually exactly what's happening. And it sounds strange, but like the surroundings get colder, which means they're this sounds so weird. I'm trying to figure out a way to even explain it. But surroundings are getting colder. That means that energy is being drawn into the system itself. So that is endothermic. So endothermic, we look at the different examples, um, the graphs in this section, and they all look like this. So we just have to label it. So endothermic reaction starts off. Just making sure it's right here. Maybe one moment. Yeah, we good. All right. So endothermic, you have the absorption of heat. All right, so I have four things labeled there: energy of reactants, energy of products. The change in H is the difference between those two. And the AE, that stands for activation energy, that is the difference between the start and the peak. And I think that's it. And let me know if you have any questions.